Hiya, Nine. So I don't have a printed copy of the worksheet, unfortunately, so what I've done is I've basically written the main parts of the question down on this sheet that I'm going to go through for you, because some of you have had quite a few questions. So hopefully you can see which bit I mean. If you've got other questions once you've gone through this video, let me know. So figure 9.1 is the drawing here, and it shows a circuit that includes 3 ammeters. The resistance of the ammeters in the battery can be ignored. And the first question asks, what is the total resistance of the circuit? So you can see that we've got a 20 ohm resistor here, and we also have a 20 ohm resistor here, and so the sum of that, because they are in series, is 40 ohms. So that's part I for 1 mark. Then it asks you to work out the reading on ammeter 2 and ammeter 3, each worth 1 mark. Hopefully what you can see is that it's a series circuit, and so the current flowing around that loop needs to be the same everywhere. So if the first one reads 0.2 amps, then both of the others will also read 0.2 amps, both worth 1 mark. Okay, let me just move up a little bit so you can see. Sorry, move my visualizer. Ooh. No good. Should probably practice this before I started the video, shouldn't I? Okay, so in the next part of the question, hopefully what you can see is that rather than 1 loop, we now have 2. So we could trace from one side of the battery round to the other through going on the top junction here, or we could go around on the bottom. So we have a parallel circuit with 2 loops, and it asks you about what the other 2 ammeters must read. Now, we know that the sum of the currents going into junction equals the sum going out of the junction, and we've got a junction here and we've got a junction here. So ammeter 1 reads 0.8 amps. Okay, that's going to go into this junction. Some is going to split and go down this branch, and some is going to split and go down into this branch. You can see that they are both 20 ohms, so they're the same resistance, so they will get the same amount of current, so they will share half each. Half of 0.8 is 0.4 amps. 0.4 would also go down in this junction loop, but we don't have an ammeter, so there's no reading. But once you get to this junction, the 0.4 that's on both will rejoin and make 0.8, which will then go into ammeter 3, which makes sense because the same current has to go into the battery as comes out of it. So ammeter 2 is this one, which is 0.4, so you're going to tick less than 0.8 amps, and ammeter 3 should read 0.8 amps. Okay, so that's question 1. Question 2 then, let's go back to this one. Let me just check and see. That looks fairly straight. Excuse me, coughing. Okay, the resistance of a piece of wire of constant diameter depends on its length. On the axes, sketch a graph to show how the resistance of the wire varies with length. So if there is no length at 0, 0, there can't be any resistance, so it will go through the origin because there's nothing there. And you should know that as the length of a wire increases, the resistance also increases. So all I need to see is a straight line graph that's increasing with y as x also increases. Doesn't matter what the gradient is because we don't put any numbers there. Okay, so you would get 1 mark for knowing it goes through 0, 0, and 1 mark for it being a straight line graph. Okay, in part B, a reel contains 50 meters of insulated wire. The ends of the wire are connected to the circuit as shown, and it looks like you've got a series loop, and then you've got a meter put in parallel over the top. So meter 1, because we know it's been connected in parallel, it must be a voltmeter, and therefore it is measuring the voltage or the potential difference across the wire. And then meter 2 is connected in series in the main loop here, so therefore it is an ammeter, and so it must be measuring the current of the coil in the wire. Let me move up so you can see part V. So you have two dials, I'm not going to draw those out, but basically in figure 7.3a you've got a voltmeter reader, which gives you 7.5 volts if you look quite carefully, and the ammeter is reading 0.3 amps. And so it asks you to calculate the resistance of the coil. So you know that resistance is voltage divided by current, so you're going to do 7.5 divided by 0.3, and you're going to get 25 ohms for the resistance of the coil. And then it asks what is the resistance per meter of the wire. Now earlier in the question it tells you that the wire is 50 meters long, so 25 ohms is for 50 meters. So all you're going to do to find 1 meter is you're going to do 50 divided by 25. Okay, and therefore you know, I've done that the wrong way around, haven't I? Oh my goodness me, sorry. My brain is slowly turning to mush. You do 25 divided by 50, and you're going to get 0.5 ohms per meter. Okay, so that's question number 2. Okay, let's look at question number 3, which is a bit more of a wordy question. So a plastic rod is rubbed with a cloth, it becomes positively charged. After charging, the rod is held close to the suspended table tennis ball, shown in figure 9.1, and it is covered with metal paint and uncharged initially. Describe what happens to the charges in the metal paint on the ball as the positively charged rod is brought close to the ball. Okay, so inside of the metal rod, before, what you would have is evenly distributed positive and negatives throughout. Okay? After we bring a positively charged rod, the electrons, which are negative, are going to be attracted, and so they are going to move towards the positively charged rod, but the positive charges, the protons, can't move, they're stuck to their atoms, so they stay in the same place, but all of the electrons, we have 1, 2, 3, 4, 5, 6 in my picture, will move towards the rod. Okay, so when it says describe what happens to the charges in the metal paint on the ball as the positively charged rod is brought close to the ball, what you will say is something like the negatively charged electrons are attracted to the positively charged rod and move to the right hand side of the ball. Okay? Okay, in part B it says the ball is attracted towards the charged rod. Explain why this happens given that the ball is uncharged. The ball is uncharged because there are the same number of protons and electrons. So overall balance to be neutral. However, the electrons, which are negatively charged, are attracted to the positive rod. Oh, sorry, it's not on the video. There you go. So the ball is uncharged because there are the same number of protons and electrons, so overall balance to be neutral. However, the electrons, which are negatively charged, are attracted to the positive rod. Okay, now in part C it says state the unit in which electric charge is measured, and that is just the coulomb. Okay, so that's for 1 mark. Sorry, it's turning into a very long video. Question 4 then. Okay, a student sets up a circuit containing 3 identical cells. Each cell has an EMF of 2 volts. Figure 8.1 shows the cells in series with a length of uniform metal wire connected between 2 terminals K and L and a resistor X. So part A is quite straightforward. If each cell has 2 volts, if they're placed in series, we add them up. So we've got 3 lots of 2. So we've got 6 volts for 1 mark there for part A. Okay, so part B, it tells you that the ammeter reading is 0.25 amps. It asks again what the unit of electric charge is measured in. That again is the coulomb. So you can see this gets asked by the exams quite often, so you need to remember that. And then it asks you to calculate the charge that flows through the circuit in 12 minutes. So it wants to know Q. It tells you T is 12 minutes, and we know that that is 720 seconds, and we know that the current is 0.25 amps. Q equals I multiplied by T equals 720 multiplied by 0.25 gives us 180 coulombs. That's for 2 marks. Okay, it'll be 1 mark for knowing the equation and 1 mark for putting the right numbers in. Okay, it now tells us that the metal wire has a resistance of 16 ohms. Okay, calculate the resistance of resistor X. Now I'm just going to show you the diagram before I move down to the space. So we know that we have 6 volts, okay, being supplied to the circuit, and we know that the current is 0.25 amps. So we have V is 6 volts, we have I is 0.25 amps, and we know that R is the resistance of the circuit, and that is going to be the resistance of this resistor X plus the resistance across this metal wire, which we know here is 16 ohms. Okay, so it's 16 plus X. Okay, I'm just going to move down here and we're going to rewrite those numbers. Okay, we know V equals IR. We know that we can rearrange that and say R is equal to V divided by I. If I plug my values in, I can say 16 plus X must equal 6 over 0.25. Okay, so 16 plus X equals 24. If I take 16 from both sides, I get X is equal to 8 ohms, and so I therefore know that the resistor X has a value of 8 ohms. Okay? Alright, question 5. In a room in a house there are 4 electric lamps in parallel with each other, controlled by a single switch. With all the lamps working, one of the lamp filaments suddenly breaks. What, if anything, happens to the remaining lamps? So, the first thing you need to do to help yourself out here is to sketch what that circuit diagram looks like. So, we have 4 lamps in parallel with each other, controlled, I'm just going to put a power supply up here, by a single switch. Okay, now obviously I'd like to do pencil and ruler, but that will make this video extra long, so for now bear with me, but that's not good practice. Okay, so this is what it looks like. This one switch breaks or closes the circuit and either makes the circuit on or off. So, if all of the lamps working and we close the switch so we look like this, then we've got a complete circuit with 4 loops and all of the lamps will be switched on. Okay, now it says one of them suddenly breaks, so let's just choose this one, suddenly breaks. What you can hopefully see is that there are still pathways around all of the other bulbs that allow charges to flow from one side of the battery through those bulbs and back again, and so nothing happens. Okay, so the first thing to say is nothing happens to the bulbs or the other bulbs. That's one mark. This is because the other lamps are on their own loops in the circuit, giving complete pathways from one side of the power supply to the other. Okay, so long as you said something about the lamps being on their own loops, that would get you the mark there. Okay, then it shows you a two-way switch diagram which looks like this one, and it asks you to complete the table by indicating whether the lamp would be on or off for each of the switch positions. So if we have a little look, I've put the 2's in the wrong place, that's a 2, that's a 2, sorry. Position of switch X is in 1, as it is shown already, and position of switch Y is also in 1. We have a complete loop of the circuit, and the state of the lamp is that it's on. If this switch remains connected here, but this one breaks and is connected there instead, what you have is now a broken circuit, because what I need you to imagine is that this bit here isn't connected. Okay, that isn't connected, so I don't have a way, because that bit would be broken now. Okay, so that one will be off. If this one is at position 2 and this one goes back to being at position 1, hopefully you can also see, I would trace round, I get down here, but this one is no longer connected to 2, so there's a gap here, so this one will also be off. And if they're both connected to 2, I would trace all the way round, and that means on. Okay, So hopefully what you can see is that there are two ways for the lamp to be switched on. So why that is useful is in a room we can have more than one switch to turn the light on. Okay, so if you've got a very big room and you've got two doors where the light switches normally are, in this case we can actually have you turning them on or off from both sides of the room. That's why that's helpful. If you've got any other questions about any of the questions I've just gone through, send me an email. Hopefully that has helped you.